Good morning all. So in today's class we look at what is called a Laplace equation and what are called equipotential surfaces. Now Laplace equation is one of the most important elliptic PDEs, so which has very much of application in physical problems. So the Laplace equation is an equation of the form del square is I equal to 0. So del square is the Laplacian operator. So that is dou square by dou x square plus dou square by dou y square, which is in the 2-dimension. 3-dimension varumbol 3 variables varum. So this is the 2-dimensional Laplace equation. Dou square is I by dou x square plus dou square is I by dou y square equal to 0, and dou square is I by dou x square plus dou square is I by dou y square plus dou square is I by dou z square equal to 0. So this is the 3-dimensional Laplace equation. So Laplace equation commonly occurs in problems of electrical, magnetic and gravitational potentials of steady state temperatures and hydrodynamics. So these are some of the physical problems where you will find the final problem to be a Laplace equation. So the solution of a Laplace equation are called harmonic functions, which you have already seen in complex analysis. Okay, appo harmonic functions aayirikkum. Harmonic functions Laplace equation satisfy cheyum. So solution of Laplace equation are called harmonic function. Now for example, so here we have one of the solutions of the Laplace equation. So that is xi equal to q by mod r minus r dash. So where r is the vector xi yj plus zk, that is r has the coordinates x, y and z, and r dash has the coordinates x dash, y dash and z dash. So if q is constant and x dash, y dash, z dash is a fixed point, then if you take xi equal to q by root of x minus x dash square plus y minus y dash square plus z minus z dash square, so you can actually see that it will satisfy the equation. So we dou xi by dou x edukumbo, you will get minus q x minus x dash by mod r minus r dash whole cube, and dou square xi by dou x square is minus q by mod r minus r dash cube plus 3q x minus x dash square by r minus r dash raised to 5. But similarly, you can find dou xi by dou x, replace x into x by y. So dou square xi by dou x square kandupidikam, adole dou xi by dou z and dou square xi by dou z. So when you add up all the three, you are going to get minus 3q by norm of r minus r dash cube plus 3q by r mod r minus r dash cube, so which will be equal to 0. So this xi here is a solution of the Laplace equation. So every harmonic function is going to be a solution of Laplace equation. So the given Laplace equation can have many different solutions. Now consider the function xi of x, y, z. So now where xi is solution of the Laplace equation. So now we will look at what is called a family of equipotential surfaces. So suppose xi is a solution of the Laplace's equation, then if you have a one parameter system of surfaces which is of the form xi of x, y, z equal to c, so such a family of surfaces is called as the equipotential surface. Given a solution of the Laplace equation xi of x, y, z, the one-dimensional surface of the form xi of x, y, z equal to c is called the equipotential surface. Now if you take any arbitrary surface, any arbitrary one parameter family of surface, so let me take f of x, y, z equal to C. അപ്പോൾ ഇങ്ങനെ ഒരു സർഫസ് എപ്പോഴും, if you take an arbitrary one parameter surface, that need not be always an equipotential surface. അപ്പോൾ surface of the form f of x, y, z equal to C, that need not be an equipotential surface always, but provided f of x, y, z satisfies certain conditions, it can be considered as an equipotential surface. So we will look at what is this condition. So let us consider the surface f of x, y, z equal to C. So I am calling that surface to be so equation 1. Now the equation 1 will become an equipotential surface if whenever xi is a constant, f of xy is also a constant. So the surface 1 will be equipotential if the function xi is constant whenever f of xy z is constant. അപ്പോൾ xi constant ആകുമ്പോഴൊക്കെ f constant ആയിരിക്കണം. So therefore we will get a relation between xi and f of the following type. So xi can be expressed as some arbitrary function of f of x, y, z. So xi will be constant whenever f is a constant. So there will be some relation connecting xi and f. So xi can be expressed as an arbitrary function of f of x, y, z. So let me call it as equation 2. ഇനി xi എന്ന് പറയുന്നത് equipotential surface ആണ്. So we will differentiate 2 with respect to x. So we will find out the partial derivative. So equipotential surface ആയതുകൊണ്ട് it will satisfy the Laplace equation. So we have dou xi by dou x equal to, so by chain rule, that is dou f by df into dou f by dou x, and dou square xi by dou x square is equal to, so use the product rule and chain rule. So first term differentiate dou f by dou f with respect to x, so that will give dou square f by dou x square into dou f by dou x whole square. ഇനി രണ്ടാമത്തെ ടേമിൽ dou f by dou x നെ differentiate ചെയ്യുക with respect to x, so that will give dou f by dou x into dou square f by dou x square. Now this is dou square xi by dou x square. Similarly you can write dou square xi by dou y square and dou square xi by dou z square. അപ്പോൾ ഇവിടെ എക്സിന് പകരം വൈയും സെഡും വെച്ച് റീപ്ലേസ് ചെയ്യുക. സോ വെൻ യു ടേക്ക് ഡെൽ സ്ക്വയർ സൈ, 3 ടേംസ് ആഡ് ചെയ്യുമ്പം, അപ്പോൾ ഇൻ ദ ഫസ്റ്റ് ടേം യു വിൽ ഗെറ്റ് ഡോ സ്ക്വയർ എഫ് ബൈ ഡോ എഫ് സ്ക്വയർ ഇൻറ്റു ഡോ എഫ് ബൈ ഡോ എക്സ് സ്ക്വയർ. അപ്പോൾ എഫ് എക്സ് സ്ക്വയർ വരും പ്ലസ് എഫ് വൈ സ്ക്വയർ പ്ലസ് എഫ് സെഡ് സ്ക്വയർ, ആൻഡ് ദ നെക്സ്റ്റ് ടേം ഡോ എഫ് ബൈ ഡോ എഫ് ഇൻറ്റു ഇത് 3 ടേംസും ആഡ് ചെയ്യുമ്പോൾ യു വിൽ ഗെറ്റ് ഡെൽ സ്ക്വയർ എഫ്. So we have del square xi equal to dou square f by dou f square, and this is gradient of f whole square plus del square f into dou f by dou f. Now we can see that on the left side you have del square xi. ഇനി del square xi എന്ന് പറയുന്നത് Laplacian ആണ്. So since psi satisfies the Laplace equation, del square psi will be equal to 0. For del square psi equal to 0, your right side will be equal to 0. So that gives us this equation. For dou square f by dou f square into gradient of f whole square will be equal to minus del square f into dou f by dou f. So that is del square f by grad f square will be equal to minus f double dash f by f dash f. So we have got minus f double dash of f by f dash of f equal to del square f by grad f square. Now from equation 3 you can see that the right hand side function, this is a function of f alone. So therefore del square f by grad f square, that must be also a function of f alone. So we started with the condition xi equal to f of x y z upper del square xi. So if you are choosing xi to be f of x y z, del square xi equal to 0 ആവണമെങ്കിൽ we must have del square f by grad f square as a function of f alone. So therefore the condition for any arbitrary one parameter surface f of xyz equal to c to be an equipotential surface is del square f by grad f square must be a function of f alone. So therefore the condition that the surfaces 1 form the family of equipotential surfaces is that the quantity del square f by mod of grad f square, it must be a function of f alone. Now the function of f alone ആയിരിക്കും. So I can replace it by chi of f. അപ്പോൾ നമ്മുടെ ഡിഫറൻഷ്യൽ ഇക്വേഷൻ ഇങ്ങനെ വരും ഡി സ്ക്വയർ എഫ് ബൈ ഡി എഫ് സ്ക്വയർ പ്ലസ് chi of f into df by df equal to 0. So when you integrate you will get, so I can write it as f double dash by f dash equal to minus chi of x. Integrate ചെയ്യുമ്പോൾ you will get log f dash equal to integral minus integral chi of f plus log a. So taking exponential on both sides, so you will get df by df equal to a times e raised to minus integral chi of f df. Ini integrating once again with respect to f, so this is what you are going to get as the solution. So where a and b are arbitrary constants. This is not dt, this is df. ഇതിനെ വീണ്ടും എഫ് വെച്ച് ഇൻ്റഗ്രേറ്റ് ചെയ്യുക. അപ്പോൾ ഇൻ്റഗ്രൽ ഇ റേസ് ടു മൈനസ് ഇൻ്റഗ്രൽ chi of f df df വരും പ്ലസ് ആർബിട്രറി കോൺസ്റ്റൻറ്റ് b. So now capital F is so we have the relation xi equal to f of f. So we have got what is our function f. അപ്പോൾ നമ്മൾ നമ്മുടെ എഫിൻ്റെ വാല്യൂ ആണ് ഈ കിട്ടിയിരിക്കുന്നത്. ഓക്കെ, സോ ഇഫ് യു ചൂസ് xi in this form, അപ്പോൾ when you are given an arbitrary function f, so if you take xi equal to a integral e raised to minus integral chi of f df df plus b. ഇപ്പോൾ ഇവിടെ chi of f എന്താ, chi of f എന്ന് പറയുന്നത് that is del square f by mod grad f square. So given an f, so if you choose your xi in this form, so this is going to be a solution of the Laplace equation. So provided f satisfy ചെയ്യേണ്ട കണ്ടീഷൻ ഇതാണ്. So f must satisfy this condition, അതായത് del square f by mod grad f square that must be a function of f alone. അങ്ങനെയാണെങ്കിൽ നമുക്കിവിടെ chi of f എന്ന് എഴുതാൻ പറ്റുള്ളൂ. Then only this will be integrable. So such a psi will be a solution of the Laplace equation. So not from given family f of x y z equal to c, provided it satisfies certain conditions, you can construct an equipotential surface. So this is the corresponding equipotential surface. So in the next class we will see a few problems for finding xi using this technique. Given a surface, one parameter surface f of x y z equal to c, we will look at how to find the equipotential surface xi equal to c.